Hello, welcome to our first Math 120 online video. Remember, you can pause these at any time you want to. I recommend that you do that frequently so that you can think and take notes and practice all the stuff that we're doing. On the quiz, the number one thing that you're doing is problem solving. So use these as opportunities to practice all the things that you're going to do on the quiz. One other little note about this. I've decided that to help you guys out on the quiz, I'm going to put a secret video question somewhere in every video. On the quiz, if you know what the answer to the secret video question, you'll get full credit for that question. Today's secret video question is secret video question. Answer. How about purple? It's going to be a multiple choice question. There will be a few different options, and if you choose purple, you'll get the correct answer. I'm going to do one of these for every video, so I'm hoping that that makes maybe is a form of partial credit. You'll get credit just for watching the video. If you know the answer, you'll get the question right, and maybe that can help your grade a little bit. So today is purple. Later on, at the end of the week, when we take our online quiz on Notable, just like regular, you'll know one of the answers to the question, one of the question answers. And I'll do this for all of the videos that we do. Purple. Okay, let's see, what are we doing today? I thought for our first video, we could do a review of sampling distributions, the thing that we've been talking about for the past week and a half in this class. Remember, sampling distributions are probability distributions for sample statistics. We've got two of these things that we think about a bunch. If we're talking about quantitative data, then the sample statistic that we think about is the mean, or the average. So the sampling distribution there tells us how likely a particular sample average is. On the other hand, if we're talking about categorical data, then we think about the proportion. What proportion of you have black hair? What proportion of you are from out of state? What proportion of you fall into any particular category? We've got a sampling distribution for that too. And in both of these scenarios, the sampling distribution lets us answer the question, how likely is a specific sample result? It's a really interesting question. It really takes our analysis of a sample result to the next level. Instead of just observing, oh, we got an average of blah, or we got a proportion of blah, we can say something mathematically supported about how likely or unlikely a particular sample result is. And that's our whole goal with this stuff. It's really important. It's the foundation for all the cool techniques that we're going to do for the rest of the semester. So let's remember what's going on. First, by the way, this screen would be a good one to pause on. All of this stuff is stuff that we've talked about before, but you might want to spend a little bit of time reading what I've got on the screen here to think carefully about everything that's going on. Just like any distribution, we care a lot about the center and the spread. What's common and how far does it deviate from that? And we need to think about both of them. Sample means, or x bar, sample proportions, or p hat. For sample means, let me highlight the most important thing and the thing I'm talking about right now. It says mu x bar is equal to mu. So in other words, our expected sample mean should be close to the population mean. In the long run, if we take lots of samples, that's what sample averages are going to target, whatever the true population mean is. Of course, we know we're not always going to get the true population mean. And that's why we need to think about the spread of this distribution too, here, sigma x bar. The spread of the distribution is how wide this thing is. How much deviation do we expect to see when we take a sample result? We're not always going to get right on the nose for the population value. We need to know how far off we're going to be. Maybe you could think of it like throwing a dart at a dartboard. If you've got my skill at darts, you're not always going to hit the center every time. Sometimes it's going to be a little bit to the left, or the right, or up or down. The standard deviation tells us something about how much variation you expect to see. Then we've got the same sort of equations for p hat. I wanted to put these together just to emphasize how similar they are. Center and spread, we care about the same thing for both of these distributions. For p hat, we have a really similar notion of center. It's p. In other words, the population proportion. We expect that our sample proportions should be pretty close to the population proportion. Of course, we know it's not always going to be perfectly the population proportion, so we need to think about the spread for that distribution too. How much wiggle room do we expect to see when we're taking these samples? The formula for the spread isn't super intuitive, square root of p times 1 minus p over n. But it's not too bad to compute. I'll show you some examples here in a second. How about, let's do an example right now. Again, make sure to pause as much as you need to stop and think about these equations. If they seem a little bit mysterious right now, don't worry, we're about to do an example. But you can control how fast this goes. Oh, sorry, before we do an example, we should talk about the shape for these things too. We've talked about the central limit theorem quite a bunch. It's the thing that we saw when we did our in-class dice rolling experiment, and it's also what your Lab 4 was all about. We know that these sampling distributions, even though they're kind of complicated and weird to think about, fortunately, we always know what shape they have. They always follow a normal distribution. Well, almost always, as long as the sample size is big enough. If we've got a big sample size, then we know x bar is going to follow a normal distribution, and also p hat is going to follow a normal distribution. What exactly does big enough mean? Well, it means slightly different things for each one. If we're talking about sample averages, we need a sample size of at least 30 to ensure that we've got a normal distribution. If we're talking about sample proportions, then we need to make sure that both n times p and n times 1 minus p are at least 10. That might seem a little weird. What it means is we need to have at least 10 that are in the category and at least 10 that aren't in the category. Again, feel free to pause on the screen. I'm going to show you right now some examples of how to use these things. Okay, so first let's do a quantitative example. In other words, x bar, a sample mean. The question here involves the mean resting heart rate of Denison students. And I'll be honest, I made this example up. I'm not sure if this is true. But suppose the mean resting heart rate of Denison students is 66.1 BPM, beats per minute. And we know that the standard deviation for heart rate is 6.2. The question here is about a particular sample result. If we take a sample of 45 students, what's the probability that the mean of those 45 is more than 68? Here's the question. Here is a quiz question. I'm going to ask you exactly the same question on the quiz. I'm just going to change the numbers a little bit. So let me show you how to decipher all of the information here. We've got 1, 2, 3, 4 different numbers in this problem. We want to think carefully about what they all mean. So first, let's think about the information that's given to us in the problem. The first sentence tells us about all Denison students. This first sentence here, it's not about a sample. It's about all Denison students. It tells us the mean resting heart rate for all Denison students is 66.1, standard deviation of 6.2. That's mu and sigma, respectively. Let's think about that. In my work, I'm going to start typing here the problem just told us that mu is equal to 66.1. And also that sigma is equal to 6.2. That's our population information. So we know what's going on with the population. The question is asking about a sample. In particular, our question that we're asking here is, what's the probability that x bar is more than 68? What's the probability that x bar is more than 68? And I think it's a really interesting question to stop and think about. We know something that's going on with the population, and we're asking, okay, how likely is this sample result? If we took a sample of size 45 students and we got a mean of 68, how likely would that be? In other words, we're thinking that x bar is equal to 68. We're using that value. That's going to be our cutoff. Our cutoff is x bar equals 68. Our sample size is n equals 45. Okay, so now that we know all the info about this problem, let's do what we always do. We know it's got to have a normal, do we know it's got to have a normal distribution? Note, since n is bigger than 30, I guess it's at least 30, we know that x bar follows a normal distribution. That's the central limit theorem. Central limit theorem says this stuff has to follow a normal distribution as long as our sample size is big enough. Our sample size is big enough, so we're good to go. You are good to use the z table. We can use the z table. But before we use the z table, we need to get a z-score. So let's do that. For our z-score, remember, how do z-scores work? It's fraction. On top, it's observed minus expected. And on bottom, it's the standard deviation. I'm going to abbreviate it like that. All z-scores work like this. We're going to do z-scores. We've been doing z-scores for a long time in this class. We're going to keep doing z-scores for a long time. And they all have the same basic format. Now here, let's think what's going on. What are all of these pieces? My observed, that's x bar, the sample result. That's the thing we're talking about actually seeing. And this problem says, it's asking us about a sample result of 68. So, poof, that's this stuff. For our expected, this stuff, what do we expect our sample average to be? Well, we saw earlier that the center for x bar is mu. I expect my sample result to be pretty close to the population. Let's write that down. For my expected, that's mu, population. And our problem here tells us that that's 66.1. We also need to get a standard deviation. And again, I'm going to scroll really quick just to show you where that is in our notes. I really want to make sure that this is clear. For the standard deviation for x bar, it's this stuff right here. That's the equation that we're talking about. Sigma x bar, or what's the spread for x bar? All right, well, we know that it's sigma divided by the square root of n. And that's the formula that I'm going to use here. On this example, we saw that sigma is equal to 6.2 there. And I know that n is equal to 45 here. So let's stick that in there. I've got 6.2 divided by the square root of 45. I'll do the math in a second to figure out what it is. But those are the only pieces we need for the z-score. Let's stick it all in and figure out what z-score we're talking about. I'm going to use my calculator here in R, just like I normally do in class. Actually, here's a good exercise. This is what you're doing on the quiz. This thing I'm about to do, this is what you're going to do on the quiz. So why not try it right now? I'm going to show you the answer here in a second, but you could pause the video, try the equation, and see if you can get it. If you got the right answer, then you understand this problem. If you didn't get the right answer, that's okay. You can watch me do it and see what went wrong. So in my work here, my observed is 68. My expected is 66.1. And I'm dividing this stuff 6.2 over the square root of 45. I'm just plugging everything in: observed, expected, standard deviation in the bottom. When I ask my calculator, we get a result of 2.05574. Cool. Here, z is equal to 2.05574. I'm going to round this to 2.06 because on the z table, everything gets rounded to 2.06. Okay, so far so good. We're not quite done with this problem yet. We've got the z-score, but we still need to figure out what's the probability of getting a z-score like that. Remember, our question was, what was our question? What's the probability that x bar is at least 68? Well, that's exactly the same thing as finding the probability of getting a z-score at least 2.06. So we need to look this thing up on the z-table. You guys have your z-tables. Remember, the z-table is in the appendix for our book too. So you can go to, I think probably the easiest way to get there is to go to the table of contents for our book. If you look at the bottom of the table of contents, there's a list of the statistical tables that we use, and the z-table is the first one. It's the same one that I printed out for you in class. If you look it up, I'm going to use the R command because here we are. But you'll see the same thing if you look up the value on the table. If you look up 2.06 on the table, I'm going to do p-norm. P-norm, let me put a note. P-norm is same as the z-table. Same thing as looking it up on the z-table. So I'm going to do p-norm of 2.06. I run this stuff. In the table, you're going to see 0.9803 because the table rounds everything off to 4 decimal places. It's not quite the end of this problem. Remember, z is greater than. We're looking for, this is a greater than probability. We want to see what's the probability of getting something that's bigger than this. Okay, cool. No problem. We just need to do 1 minus. Remember, it's greater than. So 1 minus. Here, that's 1 minus 0.9803. And that gives me, yay, a final answer of about 1.97%. There's about a 1.97% chance of observing a sample result like that, where mean blood pressure is greater than 68 BPM. And that's the end of this problem. We've answered this question: how likely is a specific sample result? That might seem like a lot at first, but once you get the hang of these problems, they all kind of work the same. You'll get your x bar, you know what mu is, you know what sigma is, and you know what n is. Those 4 numbers right here are the only ones that actually matter. stick them in, get the z-score, look it up on the table, and poof, there you go. Okay, cool. So that was a forwards problem. Let's do a backwards problem. This would be a really good time to pause, review this question, and make sure you understood this stuff. We just kind of did a lot of stuff there. Even if it made sense while I was describing it, that doesn't necessarily mean that you're going to be able to do it all by yourself. So go back through, maybe take a look at this stuff up here. Where's the problem? Here's the problem. Here's the statement of the problem. This is what you got on the quiz. Starting from this, can you do all the work that you need to do to get the answer for this? Try it out. Try it all the way to the final answer. If you get it, you're good. If not, you'll want to try again and maybe watch this part of the video again. Okay, let's do another X-bar example, but this one is going to be backwards. In this example, I'm using the same population. We're still talking about the mean resting heart rate of Denison students. And I'm using the same numbers here. It's 66.1 for the mean, and the standard deviation is 6.2. I'm going to make a little note right away, and I would do this too if I were you as a student. This problem told us mu is equal to 66.1 and sigma is equal to 6.2. That's what's going on with the population. Mu is the population mean. Sigma is the population standard deviation. Here, we're talking about a sample of size 100. First thing I'm going to do is write down n equals 100. If I was a student taking this quiz, that's what I would write down right away because that's the important information. The question says, in what range of values would we expect the middle 95% of such samples to lie? If we take, we know that not every sample is going to give us the same result. Sometimes the sample mean is going to be bigger, sometimes the sample mean is going to be smaller, but what sort of sample means do we expect to see in this thing? That's what this question is asking. It's a backwards question because it's describing a region under the curve, and we need to find out what the values are that correspond to this. I picked 95% because this is one that we've seen before. It's a backwards problem. So first, use the area to find the z-score. But we need to think carefully about what area we're talking about. If the middle area is 95%, and that's what this problem told us, we know there's got to be 5% left over. Can you see my hands? We know my head is the middle of the curve and my hands are the tails. We know there's 95% in the middle and there's got to be 5% left over for each of the two tails, but there's two of them, so we got to cut that thing in half. 5% for both of them. That means each tail area is 2.5%. Or in other words, 0.025. That's half of 5%. Now, we've got that area. You're going to find in the z-table, find the closest value. Find the closest value to 0.025. This is one that happens to be perfectly exactly in the table. If you look, you'll find this is exactly there. And in particular, you get a z-score of negative 1.96. That's the lower one. But we're always going to use both, the negative one and the positive one. The negative one is the one down below, and the positive one is the one up above. Use both. Plus and minus 1.96. Because we need to find those two cutoffs on either side of the curve. Okay, so we know what the z-score is, but we still need to figure out what the sample mean is that corresponds to this. We're using the z-score formula backwards. Remember the z-score formula for x bar. We just did this a second ago. We saw that z was equal to x bar minus mu divided by sigma over the square root of n. Now would be a good time to remind yourself, look back in your notes and see where we used this formula previously. We just used it a second ago for the first example. Now, if you solve backwards, which is what we need to do because we're looking for x bar, we need to multiply the denominator over and add mu over. I'm just going to tell you the final result. You've got that x bar is equal to z times sigma over the square root of n plus mu. I just did a little bit of algebra, but this is a formula that you can memorize. Well, by the way, you don't ever have to memorize anything for the rest of this class again because you'll always have your notes with you when you're taking these quizzes. So here's a good one. You want to have this formula with you when you're doing these things because we'll do this every time we need to find these cutoffs. Now that we've got the info, let's plug everything in. We've got, for this stuff, we just figured out that z is equal to plus or minus 1.96. We're going to do both of them. Use both. We know that sigma is equal to, what did we say sigma is? 6.2. I know that n is equal to 100. Remember, in this one, we changed the sample size. So that's a little different. And mu is equal to, what was mu equal to? Mu is equal to 66.1, right there. Mu is equal to 66.1. So let's plug everything in. Now, find x bar. First, for the lower one, I'm going to use the negative z-score because that's going to give us the smaller one. That's, let's see, negative 1.96, negative 1.96 times sigma 6.2 divided by the square root of 100 plus my mean mu is 66.1. That gives me a lower bound of 64.88. For the upper one, it's exactly the same stuff, but it's positive 1.96 because it's the one that's on the other side of the curve. So I run and I get that number. Okay, cool. What exactly does this mean? In other words, 95% of the time, we take a sample of size n equals 100. We'll find a sample mean between 64.8848 and 67.3512. Let me stick some units on that. BPM. BPM. In other words, this tells us what sort of sample result we would expect to find from a population like this. If we took a sample and found something outside of this range, it would make us think that something was going on. We call that statistically significant. This is actually called a confidence interval, which is going to be our next topic. But I think that's enough for right now. So I'll stop the end of this video. Tell me what you think. This is my first time. I'm still getting the hang of this myself. So let's get used to this stuff together and hopefully make the most of this. In our next series of videos, we're going to do some really practical applications of this technique to make predictions about what's going on in a particular population. Remember, practice this stuff. Try these problems again. See if you can start with the statement of the question, work all the way through it, and get to the same final answer that I did. If you can, you're good to go. If not, that's cool. Try again. I'll post some practice problems for you online, and you can practice those too. Remember, the secret video answer for today's video is purple. Free point. Free point. You completed this video. I'm going to stick it at a random place in each one of the videos. If you watch the video, you'll know the secret video question, and they're free points just for watching the video. So I hope that helps your grade out and makes this seem a little bit easier and more approachable. All right, guys. See you next video.